So, what's the answer? What'd you guys get?
6.
It is 6. There are 6 ways you could arrange them. Now, and I said like in a row. Like I'm not talking about whether it's like put them in a triangle formation or something like that. I mean like, what's the order that we could put 3 things? And I said letters. It could have been anything. It could have been our names. It could have actually been our bodies. And we could put 3 chairs right there. And we could say how many different ways can we sit down. They could be, letters are easy to use, right? And so one way to do this is to just enumerate them. Like I think Noah, that's what you said you did, right? And I'm curious, which was the first one that you wrote down?
ABC.
ABC, right? What's the second one you wrote down?
ACB.
Aha! That is when I do this. That's how I did it. What's the next one you did?
BAC.
Mm-hmm. That's exactly the one I do next. And then
BCA.
Yeah, BCA. And then then you do
CAB.
CAB, and then
CBA.
CBA. That's exactly the way I do it, right? And if you'll notice, and Victor, you said, isn't it? And you said it's some number. What did you say?
3 factorial.
3 factorial, which is exactly what this is. There are, and you'll notice there are 6 of them, and 3 factorial is 3 times 2 times 1, which is 6. And what Noah did is exactly how we could derive that this is the case. You'll notice he just now you could just write them in any order you want. You could just say, well, I don't know, CAB, and then I guess BAC. But that doesn't really help you come up with a method for doing it, and you're likely to not get all of them. But what Noah did, and I think what's intuitive, is, well, you choose one of them to begin with. And then, I guess either of the 2 that you do. You did it in order, which makes sense to start off with that order. And then you say, well, another way to do it would be to keep the same thing in the front, and then just switch these 2 right there. So that gives you those. And then you say, okay, we've exhausted all the possibilities where A comes first. Now let's start with something else first. We could do C, but obviously you could choose B. And so then, okay, then this is one way that the B's go first, and of course you could do it in dictionary order where the remaining ones go A and then C. And you say, is there another way we could have B first? Yes, it's where you swap these 2, and then BCA. And ditto to get your C, and then your A and your B. And you'll notice what's happening here, right, is another way of conceptualizing this is you say, well, before we choose any of them, once we choose a first letter, how many possibilities are there before we've used any of the letters? No. Just so I'm going to put one letter right here. There's 3 possibilities of what I could use. I could either put an A, I could put a B, or I could put a C. Okay. So there are 3 possibilities that I could put for first. But then once I've made that choice, let's say I choose my A's. Now there's only 2 possibilities for what comes next, right? Or like, for instance, once I choose my B, then I could either put an A or a C. Once I choose a C, I could either put an A or a B for the next one. So now there are 2 possibilities for the second one. And then once I've chosen my second one, and this is the case here, we got this one, and then, well, there's only 1 possibility for that last one, right? Or, well, I guess in every case, right? Once you've chosen your first one, call it C. And then you've chosen your next one, say it's A. Well, now there's only 1 possibility left because you're only ordering 3 things. It has to be B. So there's only 1 possibility. And indeed, what you do with all of these numbers is you multiply them together. And what we get here is 3 factorial right there, which is 6. Right? Now, do you believe that this scales up if I said, how many ways can you arrange 4 things? Yeah, because let's say we had letters A, B, C, and D. It's still the same thing. Now, we could go through and write out all 24 of them. Or we could do this type of thing where we say, well, hold up. You could think about them as sitting people in chairs, or you have 4 boxes and 4 things to put in the boxes, or whatever. You just have this, and in this space, right, this first bit, we could have any one of them say B. We choose B. Or we could choose C. We have 4 possibilities of what we could do there. Then, once we've taken one out, say we took out B, and we put it there, now there's only 3 things remaining. And so you have 3 possibilities. And let's say the thing that we chose was C. Okay. Now you have only 2 letters remaining, so you have 2 possibilities, 2 things you could put into the box. And let's say it was A. Okay, so A is gone. Now you only have 1 possibility. The only one that's left is D, and so there's only 1 possibility left. And so altogether you have 4 times 3 times 2 times 1, which is 4 factorial, which I believe is 24. You have 24 possibilities of arranging 4 things, like in a row, right? Does that make sense?
Yeah.
Okay. What we're about to do, so we're going to come back to this and we're going to flesh this out a bit more, where there's going to be some definitions and all that kind of stuff. But before we do all that, I just want to say how much I hate this topic. This is something called combinatorics, and it's a fancy way of saying counting. Like, this is how many ways can you do X and Y? I absolutely hate it. And one of the reasons why I hate it is, as you'll see in this first definition, it's so... All right, Pete, please keep it down. Please keep it down, buddy. It's so... I call it hand wavy. It's not very... It does not seem rigorous at all. And so this leads right in... These guys. It leads right into probability, which I really like the rigorous aspects of probability, but when you're actually... What we're going to do in this book, and what you'll do if you take your first probability course in college, is questions like, if there are 6 green basketballs and 2 red basketballs, what's the odds that you pick a red basketball before you pick a blue? And it's just like, I just hate stuff like that. And whereas like if it's like, probability, like the deeper like rigorous foundation for this stuff, you're talking about functions and you're talking about distributions and stuff like that. I find that stuff really cool, but this kind of stuff is just a headache to me. So we're gonna trudge through it together. Maybe you like it, maybe you don't. That's cool. So part of your homework is to read this section, 10.6, and you'll see what I mean. Like it's just. I just hate it. I just have to be honest. I absolutely hate this stuff. But it's actually good to see. We'll talk, before we actually do the section on probability, we're going to discuss something called the Dunning-Kruger effect. You can look that up if you want. But we'll discuss it briefly. And this is another reason why I hate to teach probability or anything like this. But anyway, okay. So, sorry for all that preamble. Here we go. This is what your book calls the fundamental counting principle. I'm not going to spell it out. The fundamental counting principle. Get ready. I'm going to hate this. Let E1, E2, and so on, all the way up to EK be a sequence. Nothing important about it being a sequence, by the way. Like you think, oh, it's a sequence. Okay, so we're going to talk about sequences. No, doesn't matter. Well, I guess it kind of does. Of K events. What? Okay, so K, that's the number of them. If K were 5, it would be a sequence of 5 events. Does not bother to define what an event is, which annoys me, one of the reasons I just hate this stuff. But you can think about an event in a lot of different ways, and we'll do some examples to kind of flesh all of this out. Okay, but for right now, I just want to get this up on the board. So, be a sequence of K events. If for each what? What are you talking about? Event E sub I. Okay, so when you see this in math, what this means is like any one of these. So you can think of E1, E2, and so on and so on. EI is like the general one in the middle, where you might write a formula, all the way up to the last one, which is EK. So what we've done before is usually N is the number of things that you have. So you have E2 all the way up to your general one in the middle, EI, all the way up to E. Usually N, but here they're using K, right? So that's what it's saying. So it's just saying, for any one of them, and it's just saying, here's the general one with which you might want to write a formula. So we give it a variable I, okay? So if for each one of them, so it could be I could be 1, I could be 2, it could be all the way up to K. But if for each one of them, event EI can occur n m sub I ways. I hate this stuff. I really hate it. Then the total number. Then the total number of ways that all events may occur is m1 times m2 times all the way up to m. Okay. Okay. There's no proof for this. It's just like, right? This is another reason why I hate this. It's just, we just kind of take it as an axiom. Now let's think about what we just did. We had 3 letters. And we wanted to see how many ways we could order them. And so you could think about the first event is you choose one of the letters and put it in, right? How many different ways are there to do that? So event 1 would be choose your first letter. So M1, the number of ways that that could occur, is how many different ways can we choose one of those letters? There's 3 ways, right? And this is all they're saying here, right? And so event 2 would be now you choose your second letter. Since we've already chosen one, how many ways are there now? What is M? What is the number of ways that we could choose the second letter?
2.
It's 2, right? And so on with E3 would be that you choose your second or you choose your third. And now, since there's only 3 things, of course there's only one way of doing it. And so the total number of ways that all events may occur would be M1 times M2 times M3, which we already said was 3 times 2 times 1, which is 3 factorial, which is 6, right? So that's what this is saying, okay? And it's a fundamental counting principle. Now, one thing I do want to warn you on, there's a very big difference. Now, you might think that all of your questions are going to boil down to this type of thing, where you're going to have something, and then the next ways that it could occur is going to be less, and then the next ways that occur is going to be 1 less. Sometimes, maybe, but what if, and like Victor said, can we repeat these? What if there are repeats? What if repeats were allowed, right? Can you choose one, and now, like, can you go A? Can you go B, or A, B? Well, that's different. And let's go ahead and do that. Let's say that repeats are allowed. How many ways could you choose your first letter?
9.
Whoa. Just one. You're choosing one of these. It's still 3. Now, how many ways can you choose your second letter?
Still 3.
It's still 3.
Still 3.
And it's still 3. And so M1 times M2 times M3 would be 3 to the third, which would be 27. Okay? So this is the fundamental counting principle, right? And it does make sense. I can't see any other way that it could be. So it's like an axiom, but again, how could you prove that? I don't know. Maybe there's a course, in some course you take, you would actually prove something like this, but I don't know. Maybe, right? But I mean, this is the thing. You were talking about like real world events. In fact, we're about to do a very concrete example of something. And it's like, how could you prove that math faithfully maps onto these events, or that these events in real life faithfully map onto the abstract world of number? These are way beyond my pay grade, right? And way beyond a mathematician expertise. We're in the realm of philosophy, possibly theology. Yeah, this is serious. I'm dead serious here. So, okay, in other words, this fundamental counting principle, you could put it this way. Multiply the possibilities of all events. Right, that's all that is. And that's really what it comes down to, is that you multiply these possibilities. You're not adding them, right? It's not 3 plus 2 plus 1, which happens to be 6. That's funny, right? So like, how many different ways were there to, if you could replace them, then we said that there were 3 each time, so you get 3 times 3 times 3. It's not 3 plus 3 plus 3. So that's the principle there, is that really what this comes down to, like obviously it has something to do with the numbers of ways you could do it, but what do you do with them? Do you add these ways together? Well, the fundamental counting principle says that you multiply them. Kind of makes sense. Okay, so here's a concrete example. This is number 17. And yeah, I'm doing an odd one as an example. Oh, by the way, okay, I said your homework's to read. So now, page 785, 1, 5, 11, 13, 21, 23, 29, 33, 35. That's your homework. Okay, all right. Okay, 8 basketball teams. There are 8 basketball teams in a tournament. Find the number of ways that first, second, and third place can be decided. Now, be decided. Like it's how the book puts it, but you know what that means. Like, how many different ways can these teams win? You know, like how many ways could this tournament go, right? And one thing it does say is that no ties, assuming no ties are not allowed. Yeah. No ties. In other words, there can only be one first place. You can't be in both first and second place, right? Or whatever. You can't have 2 people in first place, right? So, given that you have 8 basketball teams in a tournament, okay. Now, one way you could do this. So yeah, go ahead. If you have something to say.
Would it be 8 times 7 times 6?
Yes, it would. Yes, it would. And it's this counting principle. And we could think about it as you have 8 things, right? You could think about, here's the 8 basketball teams. Let's name them A through whatever it would be. I guess G is 7. G comes after G. H. Okay. Okay. Yeah. So you have the teams A through B. Well, what are the possibilities? And so it's like, it's the same question really. Like abstractly, you could say, this is the same question as you have 8 people and you want to arrange them in 3 chairs. You have 3 you're playing musical chairs or whatever, right? And like, how many different ways can this work out? Well, there's 8 possibilities to go in chair number 1. There's 8 different possibilities that you could go into first, right? Now you've gotten rid of one of them. You have 7 left over. And so how many different ways can you have a person in second place? Well, there's 7. And how many different ways are there? Well, now that you've lost another one, now you only have 6 teams remaining. And so who could be in third place? Well, there's 6 possibilities. And that would be 8 times 7 times 6, which I think is 336. And so that's the answer. That's what it's looking for. That's what the back of the book is going to say right there, 336. Everybody got that? Yeah. Okay. Now you'll notice this is not 8 factorial. It's not 3 factorial, right? Earlier on, when we were using every single one of those things, then we had something to do with factorial. We'll get into this in just a second. Just something to note, okay? And so no ties means no repetitions, right? It's the same kind of thing that we saw earlier. The first question you asked was, can we use A twice, or can we use any of them twice? Can they be used multiple times? We call that repetitions. And so no ties is a way of saying in the context of this problem that you cannot repeat, right? There's no repetitions of any of these. What if there were repetitions? And that doesn't make any sense in terms of basketball teams. But let's say you have 8 things, you need to have 3 of them, and repetitions are allowed. Then how would you go figure this out? How many possibilities for the first one?
8.
And then for the second one?
And 8.
8, 8, and 8. Yeah. So it would be 8 to the 3rd or whatever. Which is whatever. Okay. It's a big old number. 64 times 8. Okay, so there's that. Here's another example. Here's an example I made up. And this is kind of this, I kind of like this kind of stuff. So it's not that I hate all of this stuff. It's And it's not that it's not useful, it's very useful. But allowable characters for a password are lowercase a through lowercase z and 0 through 1. Now I could have made this hard, so a through z. And we could actually figure it out. Lowercase a through lowercase z, uppercase a, uppercase z, 0 through 1, and then all the special characters. You could figure that out, right? And then, okay. But here we are. The allowable characters for a password are this. Okay. How many, and so here's the question. How many 4-digit passwords? You're going to stop me and be like nothing in the world is going to let you do a 4-digit pass. And yes, of course, but I'm trying to make this like where we can actually calculate this. It's not too hard, right? How many 4-digit passwords are there?
With or without repeat?
There you go. Then that's the question. First is without repetition. Repetitions. And 2, with repetitions.
Well, with it would just be 26 plus 9. Or
Is
plus
that-
10. That was a 1.
Oops, that's a 1.
It'd be 26 plus 9 to the 4. Or plus 10.
Is that 9? How many are these?
10. Because
No,
it
that's
includes
10.
0.
It's because it includes 0. 1 through 9 is 9, and then 0 is 10.
It'd
So,
be 36 to the 4th.
36 to the 4. So let's, and this is how I like to do this, okay? I have to do it this way, right? There's 4 bins that we're going to fill up. And this is, we're doing with repetitions, okay? There's how many possibilities for the first one? 36. And then how many for the next
36.
one? It could be 36. And then how many?
36.
Still 36. So this is 36 to the 4th, which is 1, 6, 7, 9. 616. 1,679,616. Okay. Now, without repetitions, we have 4 bins to fill up. How many things can we put in the first bin?
36. 35.
Then 35.
34.
Then 34. Then
33.
which works out to be 1,413,720. Okay.
You can see why. Yeah.
Now you'll note. Now here's an interesting thing. This type of question, you'll notice that there's more possibilities if repetitions are allowed. But this is exactly the type of thing that when you go to make a password, they don't let you do. Like, if you go to make a password, right, it says, and with actual passwords, the characters are A through Z, capital A, capital Z, and the special characters, right? So like this, at, $, etc., right? And then they tell you, now if you just figure out what the total things are, and let's say it has to be a minimum of 8, and you say, okay, 26 and 26, that's 52, plus the 10 from these guys, plus, let's just say it's 10 special characters, whatever. So 52, 10, and 10 is what, 72. And you'd say that, well,
2 to the 4th.
well, yeah, and let's do the 4th, right? So let's just say it has to be at least 4 long, right? Whatever. So that'll be 72 to the 4th. Now, you'd think that's a really big number, but when you start the way that passwords actually work, they say you have to have one uppercase, you have to have one lowercase, you have to use a special character. Well, that starts to whittle these down, right? The same way that I said up here that no repetitions are allowed, that whittles down the number. And so you'd think, well, there's more possibilities if you let me do whatever I want with those. If you let me repeat, if you let me say just do all lowercase a's, that's a possibility. But if you exclude that, then a hacker or somebody trying to get your password would know.
They try first.
And that's what it comes down to, is that the way the algorithm, like that brute force attacks work. This is what's called a brute force attack, where you program a computer to just pop out a bunch of different passwords. One of the ways they do that is the algorithms they use will get all of those first. Like it's quicker to go through and get those. If you can ensure that it does contain one of these and one of these and one of these, then you have to write a more complicated algorithm, and it takes longer to cycle through all of that stuff. Whereas most people left to their devices would just use lowercase numbers or lowercase letters and maybe one uppercase. And so then you could, if you're writing an algorithm, you could say, well, forget about all that. And now instead of searching through 72 possibilities, I only have to do 52 to the fourth or whatever, which is way, way, way less. But so it's weird. It's really weird. It kind of bugs me. I'm like, why can't I just do all lowercase a's? Somebody's going to try to hack my YouTube right now if you like, it's just lowercase a's. But you know what I'm saying? Because you think, well, there's more possibilities if you let me do whatever I want with those. But as you start to put restrictions on them, you actually lower the number of possible passwords. But it comes down to the algorithm that's used to brute force or to guess passwords. Right? So, interesting. That's one of the things I like about this kind of stuff. I think it's kind of cool. But okay, here we go. So, definition. A couple definitions here. Definition. Let S be a set of n elements. Let R be between 1 and n. So R could be 1, it could be n, it could be any number in between. Okay? Here's the definition part. A permutation. A permutation of R elements of S. So this is kind of like what we did with the basketball teams, right? N was the number of basketball teams. You have a set of basketball teams. How many are there? Well, there were 8. And we wanted to know, given how many, 3 of them, this is the kind of thing that we're talking about here. So you're taking some number from a set. And here's the definition. A permutation of R elements of S is an arrangement without repetition without repetitions of R elements. Okay, so just like we did with the basketball teams. We had a total of 8 basketball teams, all the way up to H, and we wanted to take any 3, we wanted to arrange, right, order 3 of them. That would be permutation of 3 elements from an 8-element set. Okay? That's just the name of it. Now, very often, when R is equal to N, then cool stuff happens. Here's an example.
Then it's like factorial, right?
Yeah, it just works out to be factorial. That's exactly what it is. But here's the thing. So if you remember, I think it was day 1 of last year, I think I defined a function.
Yeah.
And the thing that I defined, the very first function that I ever defined, I said, okay, you know what we could do? We could come up with a secret code. Like, if you're going to write a secret code to your friend, right, you can say, okay, you know what, you agree ahead of time that instead of writing A, I'm going to write the letter Q. And instead of writing B, I'm going to write the letter H. And instead of writing C, I'm going to write the letter Y, and so on, all the way down. There's Z goes to, I don't know, how about F? Right. Now, first off, it wouldn't make any sense to have a bunch of repetitions here. Because you wouldn't want both C and L to map to Y, because you couldn't make sense out of a message, right? If I see Y, H, O, how do I know it came from L, or how did I know it came from C? So that's not going to work. It has to be without repetitions, right? And this would be you could see this as a permutation of this set. Here's your set, And this would be a permutation of it. In fact, you could write it in dictionary order, A, B, C, all the way up to Z. And you could say, okay, there's your set, and we could permute it. I'm saying all this to kind of give you a sense of how these words are used as moving on, right? If you take that set and permute it, then what you get is the same exact elements. They're all exactly the same. There's no repetitions, because there were no repetitions in the first one. And you might ask, well, what happens if there is a repetition in the first one? Great question. I have no idea. I don't know how they define that. And that's one thing I hate about this topic, is that like there's so many questions that I have that just aren't really addressed. And so maybe in a more advanced thing, they would like boil that down and say, okay, all of this works only if S has no repetitions to begin with, but they never say. So anyway, we're just going to assume that's what they mean. There's no repetitions in this set. And so you permute it and you get a new order, right? A new arrangement of stuff, but you end up with the same stuff. That's when R is equal to N. This turns out to be, there's something, so if you go on in math, you'll end up taking something called, it's either called modern algebra or abstract algebra. One of the topics in there is something called group theory. Group theory. And permutations are central to group theory. Like, it's a very big thing that you talk about in group theory, and this is one of the coolest things I've ever studied, by the way. It's really, really cool. It shows up in a bunch of crazy places, like general relativity. There's a bunch of permutations of stuff. And that's like all throughout physics, there's crazy things that can be seen as permutations of other things, and it's just really, really cool. So anyway, just wanted to say that. So, permutation. Right? It's an arrangement without repetition. And a permutation of R elements of a thing is an arrangement without repetitions of R elements of that thing. Okay? So that's the definition. Now here's some notation. Notation. P and R denotes. And notice this is a function. This is written to be like a function, right? One of the inputs is N, one of the inputs is R. If you wonder what they're standing for, it's this right here, right? It's like you have a set of N elements and you're going to permute R them. It denotes the number of permutations of R elements of an N element set. Okay. Everybody got that?
Yeah.
Kind of. Let's make it concrete.
Wait.
Oh.
Yeah. Never mind.
Okay. So now we're gonna make this concrete. So P 8 3. This would be how many permutations are there if you take an 8-element set and you arrange the number of permutations. So you have 8 things, and we want to arrange 3 of them. This is the very first problem, or I'm sorry, this is one of the first problems we did. This was the basketball team problem. You have 8 teams. How many ways can you order 3 of them? Well, as we saw, that was 8 times 7 times 6. Right? Okay. Okay, so let's do another one. 36, 4. So this is, you have 36 possible elements. This was the password problem.
It would be 36 times 35.
There we go. 36 times 35 times 34 times 33. Okay.
So
now, P3, 3. Ooh. This was the very first thing we did. You have 3 things. We called them A, B, and C. And I asked, how many ways can you order all 3 of them?
3 times 2 times 1.
3 times 2 times 1. Okay? And so that's what this is. And in general, now, let's take a look at what this is. So let's come up with the formula for the general one.
Would it be n factorial minus n minus r? No, over
Not
n.
mine. Yeah. So good, so good. What did you say? N factorial.
Over n minus r factorial.
N minus r factorial. Because you can't subtract it off.
Because it just isn't, like for P83, it's just 8 factorial minus 5 factorial.
Is that 8
Wait.
factorial minus 5 factorial?
No.
No,
Yeah,
it's you divide it off. Exactly. That's exact. In fact, we were going to build up to this, but that is it. The way to get rid of it. Okay, so let's do it that way, right? That right there. And I do want to do it this way. P83. We know is 8 times 7 times 6, but if you wanted to write it as a factorial, right, you'd say, well, that looks a lot like 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but I need to get rid of these. You can't just minus them off, right? Right? So like for instance, right, 10 times 9 minus 8 is not the same thing. You know what I mean? Right? It's like, to get rid of them, since they're all multiplied together, we need to divide them off. And so we would divide off all the parts that we don't want, which is 5 times 4 times 3 times 2 times 1. So in other words, that's 8 factorial over 5 factorial, but 5 doesn't occur in either of those.
Yeah, so 8 minus 3.
So it turns out that 5 is 8 minus 3, and so we could rewrite that as 8 minus 3 factorial. And that's where that comes from right there. Okay? Everybody got that? And so this is a very nifty little way. So in other words, so this is the permutations, the number of permutations, of what? Well, if you have a set of n things, and you're going to take r of them, and that's what you get. Now let's just check that this works with that, right? Because 3 should be 3 factorial. It's 3 factorial. The permutations of 3 things chosen from a set of 3, we know it's 3 factorial because we worked that out, but the formula here says that it's 3 factorial over
0.
Yeah, 3 minus 3 factorial, which is 3 factorial over 0 factorial.
What's 3 over 1?
Which is just, it's not 3, it's 3!
Yeah,
Right, 3 factorial. Right. So, yeah, so it works, right? Like, this actually works. What I was gonna do, you just jumped right to the chase because you guys are smart. But what I was gonna do is this right here. Because this was the way that we've been doing it. So P and R means that, okay, we're trying to order R things, right? And you're starting with N of them, just like we had 8 basketball teams. And so we have R blanks to fill in here, right? Whatever R happens to be. And then, well, you're choosing from N things, so you have a possibility that the first thing, there's N of them, right? Just like before, right? Like when you had the 8 basketball teams, you're choosing 3 of them. Well, I shouldn't say choose, because next time we're going to get into something that we're actually choosing. It's different. But we're trying to find how many ways can we order these. Well, when there were 8 of them, we started where there's 8 possibilities for the first one, leaving 7 left over, then 6, right? And so here you have N and R, so you have N possibilities for the first one. Multiply that by, well, now you have N minus 1 of them left over. Now that you've taken those 2 out, I guess you don't have N minus 1, you have N minus 2 left over, right? Just like this. And so on, all the way down to, well, let's just do it this way. N minus R, how about plus 2? N minus R plus 1. It'll be N minus R. N minus R minus 1. N minus R minus 2, and so on and so forth, right? That would be N factorial, right? right?
Yeah.
And so, and that's the thing, and this was what we would need to divide off, because since you're only choosing R of them, and this is what's kind of weird. Did you guys actually look at my solutions from last night?
Yes.
Did you look at the extra credit one?
Yeah.
Okay. And so this is what I meant for the extra credit, and I'll look at how you guys did it. I haven't even looked at the quizzes yet, and if you interpreted the question differently, that's totally fine. But the thing is, we know that we only need R of these, and so you might think, we're going to keep him because look, there's R, right? It's not quite the case, because if you look at it, this is the first one, but this is n minus 0. This is n minus 1. This is n minus 2. All the way down to n minus r plus 2, n minus r plus 1, n minus r, and so forth. But we could rewrite these as n minus r minus 2. Yeah?
Yeah.
N minus r plus 1 is the same thing as n minus r minus 1. And this would be n minus r minus 0. And then if you start to count these, you say, well, this is 1, this is 2, all the way up to r minus 1, and that's r, but he's in there too. Right? This is also one of them. This is, in fact, the first place that you filled. And so we'd have to shift all of these over. This would be 1, this would be 2, this would be 3, and so on until you get up to this one, and that one would be r. Right?
Yeah.
And at the very bottom, I kind of started rambling with my answers, but what I was getting at was like, it's the same kind of problem if you're going to do like numbers 1 through 21 odd. You know, if you're doing 1 through 20 odd, you think, well, it's 1 through 20 would be 20 problems. Half of them would be 10 problems. I'm doing 10 problems.
Not.
It's not the case with 1 to 21.
They're both odd. Yeah.
Yeah, and so you think, well, 21 minus 1 is 20. Divide that by 2 is 10. That's how many problems I do. But you've lost the first one, right? By subtracting off the 1, it's like you're not counting him. By forgetting about that 0, you're not counting him either, right? And so you need the first R things. And so that's the first R things, because you have 0, 1, 2, right? You're always one more, so when you're at R minus 1, you've actually counted a total of R things. Right? Does that make sense?
Yeah. Yeah.
Yeah, right? And so, in other words, he's the first, he's the second, he's the third, and the rth one would be that one right there.
Yeah.
And so then it's like, well, then what do we need to do? What do we need to divide off in order to just have this? Because that's what we're looking for right there. Right? The same way with the basketball team, right? When we wanted to find, you have 8 teams, and you want to order 3 of those teams. How many different ways can you order 3 of those teams? You go 8 times 7 times 6. But it's like, that's not easy to compute. We would like a nice, nifty, compact way of writing that. And it looks a lot like 8 factorial, but we need to get rid of all these other bits, right? And so then the question is, what do we divide by? Well, all of this stuff is what we need to divide by, and all of that stuff happens to be n minus r factorial.
Yeah,
so then all of these cancel out, and you're left with the bit that we care about.
Yeah, okay.
Right?
That makes sense.
And so, and just to make it really concrete here, it's like, this is the number we want, but I would like to be able to write it in terms of factorials. It looks a lot like 8 factorial, but 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And so I only want 3 of them right here. And so I need to get rid of that many of them. How many is that? Well, if the total number is 8, and I know it's the tail end, right? Then I could say it's 3 is what I want. That's the number I want. And so if I say 8 minus 3, that's how many are left right here. Right? This number right there is 8 minus 3. There's 5 of them. And so it's 8 minus 3 factorial, or 5 factorial, that needs to cancel out. And so that's why we get this right here, n factorial. But that's too many. You've tracked on a bunch that you don't want, so n minus r factorial right there. Does that make sense?
Yeah.
And so the question that I was asking, and it's not, and the reason why I did it on the extra credit, let's look at time. Oh, we're good. So the reason why I did this on extra credit, which was just to so everybody recalls, you have n choose k. We're assuming that k is less than n. And the question was, and the way I worded it, I was like, I don't want to give too much away here because you need to know this formula, and I could have just said, like, cancel out the n minus k part, right? Cancel that guy out, like from there, and then I would ask you the question. You could have interpreted it as, well, that's an easy one to cancel too. You just take off the k, the last k of them. Okay, but when I was, yeah, and I understand, and I'll grade it accordingly, but you know, this is the same kind of thing. We have n times n minus 1, n minus 2, all the way down to n minus k plus 1, n minus k,
Yeah.
n minus k minus 1, all the way down to 2 times 1 over k factorial. And then n minus k factorial is n minus k minus 1, n minus k minus 2, all the way down to 2 and 1. Those all cancel, and so on and so forth until we get to there. And then that was my question. And so I could have really just started there. And the reason why I'm doing this has nothing to do, well, I mean, it's obviously it does have a lot to do with what we're doing here, but that's not why. This will come in handy later when we want to prove something big. We want to prove something that we really, really, really need to prove before we move into calculus. At least as far as I'm concerned, we need to prove it before we get to calculus. And so this will be, knowing how many of these things there are will be paramount to our proof. And I want you to believe that there are k of these things up here. Obviously there's k down here, because how many things are in k factorial? K, right? That's how many integers you have down there. You have 1, 2, 3, 4, all the way up to k. Okay, cool, so there's k of them down there. Now that is the question right there, is how many of those remain? And so, right, what I was saying, the hard way that I did it is saying, well, if this one's 1, and if this one's 2, and if this one's 3, you'll notice it's always one more than this, right? So, not that you need to, but you could rewrite it like this if you wanted to, just to help you count. So that n minus k minus 1, that's that, right? N minus k minus 1 is the same thing as that right there, right?
Yeah.
If you distribute the minus, you get that. It's just a nifty way of writing it so that everything's consistent here. And you could say, okay, well, if 0 pairs with 1, and 1 pairs with 2, and 2 pairs with 3, then k minus 1 pairs with 1 more than it, k.
So there's k.
So there's k of them, right? So it's like, or you could say, well, 1 up to k minus 1 is k minus 1 of them, and then you have the 0 that you didn't count, so that's an extra one, so k of them. Yeah. Another way of doing it is you could say, well, hold up, you had n of them on top, right? So like, for instance, I could just say this. You have 5 integers on top. You know you're canceling 3 on the bottom, so that should leave you 2 on the top, right?
Yeah. Oh,
right?
So it's just gonna be
Right? It's really like, and this is the thing, right? This is 4 times 3 times 2 times 1. And then you're just, well, how many of them have you canceled?
It'd be n minus k.
There you go, right? And so it's like, so we're not looking at this right now. It's just like, I had n on the top, the number up there was n, the number on top is n. And then how many of these do we have on the bottom? And each one of them is going to get canceled, right? Because that's less than the top. And so you're in some kind of thing like this. You have some big number, and then eventually the bottom catches up. And so the number on bottom is whatever n minus k is. And so then if you've taken some number, say 5, and you minus off 1, to 3 of them. Each one of those gets canceled off. Then you're left with 2, right? 2 numbers on top. That's the same kind of thing here. Your number on top was n. And you minus off whatever the number on the bottom one was. The number on the bottom is n minus k. And so you have n minus n plus k, which is just k. So you have k numbers left on top. Believe it or not, that's going to be hugely important. But what's interesting now is, and this is really, I mean, it's obviously related because this is almost the same thing. You'll notice, look at this, that's n choose k. And if I just simply get rid of him right there, we have this new thing that we've just defined. This is p n k right there. Right?
So it's just another function that's like.
Yeah, it is it's almost, you'll notice it's almost exactly the same as n choose k. It's almost exactly the same thing. And it's really important. And remember how we even got to this point. Why did we care about him in the first place? Because you're talking about, like, you have a set of n things, right? So let's make it concrete. 5, 3. You have a set of 5 things. A, B, C, D, and E. And now you want to fill up 3 blanks. And we want to know how many different ways can you do that if you can't replace these guys. Well, in the first place you could put 5 of them in. Now that you've chosen one, there's only 4 left over. And so how many could go in here? Well, 4. Now you've chosen another, and so there's only 3 left over. So how many could go in here? Well, there's 3 possibilities. That's 5 times 4 times 3. Turns out, right, that it's really, really beneficial to us if we could write these as factorials. And this looks like 5 factorial. We're just missing some bit, right?
Yeah.
And so it's like, if I need to write this is what I want. This is what I want. This looks like 5 factorial, but now remember, like, this trick that I brought up last year is, like, as long as you multiply and divide by the exact same thing, then you haven't changed the actual number itself. And so if I need to turn this into a factorial, which will make my life easier, well, I'll just finish up the factorial. Then it's just a matter of, well, how can I write that with those 2 numbers? How did you get this in the first place? Well, you needed 3 things on top, right? Your total number on top needed to be 3. And so you need to cancel off that many. How many is that many? Well, it's whatever 5 minus 3 is, right?
Yeah.
And so how do you get 5 minus 3? You go 5 minus 3. That's what it is. It's 5 minus 3. That's what that is, you know? And so, yeah, 5 minus 3 factorial. That's where all that stuff comes from. Okay? And it is very much related to the binomial coefficient. The only difference is that we're throwing a k in there. And we'll see why you do that in the first place and how that comes into everything that we're talking about in terms of, like, choosing things, right? Now, what we've done up until now is you say, how many ways can we put things in order? That's what we're dealing with now, and order matters. And we'll see how this changes when order doesn't matter on Thursday. Okay. So, any questions on anything?
Can you graph these functions?
You absolutely can. Actually, well, so the thing is, you'll notice this is only defined on integers.
Oh.
Right? So, like, what would 3.5 factorial be? Well, there's a thing. And so there's a function. And so x factorial works as long as x is a whole number, right? In fact, positive whole number, 0 or bigger. But what you could do is say, okay, well, there is a function. It's called the gamma function. Gamma. And annoyingly, it's not gamma of x. This is the most annoying thing. It's actually gamma x plus 1. And what happens is, when x is a whole number, this works. But gamma itself is defined on all real numbers except for the negative integers. The negative integers blow up. And so what this looks like, if you were to graph the gamma function, ooh, isn't at 0? Because you see, it's this plus 1. It is the bane of everybody's, like, everybody hates this. It's like, why the people who initially defined it did this plus 1 thing is the most annoying thing in the world. But let's pretend it's not plus 1 just for the sake of graphing. 0 factorial is 1. There's 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. And so on. And so there's something called analytic continuation. An analytic function, pretty much every function you've ever seen up until this point is an analytic function. Analytic functions are very well behaved. They do things that we like. And so there's something called analytic continuation, where if you have a bunch of points, it's kind of like this, but if you have a bunch of points like this, there is one and only one way to connect all these dots so that the function you end up with is analytic. Now I could connect these any way I want. I could just, start doing sine waves and stuff like this and say, oh, okay, I'm going to do that. But then the resulting thing would not be analytic. It wouldn't have all these nifty properties that we love about functions. And once we do calculus, once we get to a certain point in calculus, I can actually tell you what an analytic function is very succinctly, and you go, oh, okay, cool. And I'll do that, and you'll go, okay, cool. And, whatever. But, so, given a bunch of points like this, there is one and only one way to continue this to be an analytic function. And what it looks like, it's called the gamma function. It does this, and it drops down, there's a little minimum right there, and it pops up. And then there's, like, asymptotes, and they do this. And these asymptotes are at the negative integers. Oh, oops. And so it does that.
Because even factorial is negative, so it looks like kind of like secant or something.
Yeah, it does, although it doesn't, these get closer and closer to the origin. I haven't drawn that very well. Yeah, and so like the same way that this kind of follows a thing, this thing these kind of approach the thing. So it starts off like that, and then it gets closer, and then this one gets closer, and so on and so forth. So it looks like they're getting closer and closer. I think, pretty sure. And they're not like nice and symmetric. They do this weird thing, like you see how I've kind of drawn it, like, and then it drops off fast, or comes over and then drops off or whatever. This is also kind of the same way, but it's called the gamma function. And it is defined on all real numbers except for the negatives where it blows up, right? Just like secant's defined on everywhere except for where it blows up. And it is equal to the factorial function on all of these integers right there.
So what is like 1/2 factorial? Like, can you not?
Well, yeah, it's a 1/2 factorial doesn't make any sense.
Yeah.
But gamma 1/2 makes sense. So it's not like 1/2 times 1/2 minus 1, 1/2 minus 2. It doesn't do that. But what it does is that it lines up right here on this one analytic function, the one and only function that could possibly connect these points and give you a function that's analytic. So there is a way. There is a way of talking about, well, what if you factorialed 2.5? Well, there's a thing, and it's between 2 and 6. There's a number between 2 and 6 when you plug it in. Like, you take, and again, there's that weird shift thing, which is just a total pain. But you plug in 2.5, and you will get out a number that is between 2 and 6. It's just like 2 factorial is 2, and 3 factorial is 6. And so you take a number that's between those, and you'll get out a number that's between 2 and 6.
So how are the lines that connect them computed then?
How are the what?
How the lines?
You have to take some serious math for that. It's crazy. There's a bunch of different ways of doing it, but it comes down to the way that this one in particular is done is think about n factorial is equal to n times n minus 1 factorial, right?
Yeah.
And so in other words, you have some function where you plug in an n, and it's equal to n itself times f of the previous thing. This is what we call a functional equation. This tells us how f behaves. And you could say that f of 0 is equal to 1. And with this information, you could do some magic, and out pops this formula for what we call the gamma function. And it's oh, do I remember it? Ooh. X to t, no. T to x minus 1. So, I don't remember. It was one of the coolest things I learned in college, the gamma function. I loved it. It's so cool. The way that it's done. Like you start off with this and say, well, this is what factorial does. And so we're looking for a function now that's not just defined on the integers. We want it to be defined on all real numbers. And so then you could do some magic and say, and then out pops a formula for it. And it turns out that since the formula that pops out for this thing turns out to be analytic, then it's the one and only analytic function that does work. And that's just a cool thing about analytic continuation. There's only one way of connecting dots. It's just, that comes like, when I say that, like there's one way to connect these dots so that the thing that you get is nice. It's not that you're connecting every single dot together. What that comes from is there's a theorem that says that if you've done this thing, like this, you do this and then you do some magic and out pops a formula. It turns out that if that formula is indeed analytic, the function, the thing that you get is analytic, then you could, then that's the only way to do it. And there's a theorem for that. And you just take complex analysis and see just how cool it is. So it's one of the most beautiful things you could learn in mathematics is complex analysis. And all of this comes from complex analysis. And it's just beautiful, beautiful. Like the way that it all works. It's so simple. And it's just like, oh yeah, it has to be. Oh, cool. It's just, yeah. Anyway. All right, I've rambled way too long.